Okay, this is our work and energy review, so get excited about it. So the first thing that we're going to look at is just our basic definition of work. Work is, or in last year especially, was force times distance. So, just as a point, if my force is not in the same direction as my distance, I just want to look at only the part of my force that's in the direction of my distance. Only that parallel part of my force. So in terms of force and distance and that angle, work is going to be force cosine theta, that parallel part, times my distance. That's going to be my work. So our possibilities are positive work, negative work, and work equal to 0. So positive work, in that case, my force is in the exact same direction as the distance that I move. Negative work, force is in the opposite direction, so the force opposes my motion. When that happens, that force does negative work. And then we get work equal to 0. In that case, the force is perpendicular to my direction, so it neither assists my movement or opposes my movement. It's immaterial. It doesn't matter. It doesn't do anything to my movement. So if I'm sliding on flat ground, the normal force is going to do 0 work. So net work is the sum of all my forces added together. Net work is also equal to the change in the kinetic energy of the object. So this is really important. Net work is the quantity that changes the kinetic energy of my object. Anytime we do kinetic energy, anytime kinetic energy is not 0, work had to have been done. Okay? So, if I have positive net work, that means I get a gain or an increase in my kinetic energy. If I have negative net work, that gives me a decrease in my kinetic energy. I lose kinetic energy with negative work. Negative work takes away kinetic energy. Work is not a vector. This is kind of tricky. Work doesn't have a direction, but there is positive work and there is negative work. And the reason there's positive work and negative work is because positive work increases kinetic energy, negative work decreases kinetic energy. Positive work increases energy, negative work decreases energy. That's what positive and negative mean. It doesn't have anything to do with the direction. You can't say work has a direction. So, work equals force times distance is only okay if the force is constant. If the force is not constant, if my force changes with time or displacement, especially with displacement, then I cannot use that anymore. That's only true for constant forces. So if my force is somehow dependent on my displacement, things get crazy. I got to take an integral. Work would be the integral of my force with respect to displacement or distance. We'll say the integral of F with respect to R. So for right now, all I need you to know for integrals is the power rule for integration. This is the easiest one. And just in general for integration, it is the opposite operation of taking a derivative. Okay, it's the opposite of derivative. So the power rule for derivatives, if I take the derivative of x to the n, it gives me nx to the n minus 1. So if I'm going to do the opposite of that, if I'm going to take the integral of x to the n with respect to x, instead of taking away a power, I'm going to add a power. And instead of multiplying by that exponent, I'm going to divide by the new exponent. So we'll run through a really quick example. Sorry about that. I wanted a white background for some reason. So we'll run through a really quick example. In this quick example, we'll just say our force is equal to 3x squared minus 2. And what we're going to do is get my work function from that function of force. So we'll plug in 3x squared minus 2, where f was. We're doing that with respect to x. Now the nice thing about integrals, just like differentiation, is that that operation applies to each part of it. So what I'm doing is taking the integral of 3x squared dx plus the integral of 2 dx. So for the first one, we're going to do the power rule. The 3 is constant, so it comes out. And what we're going to do is take the integral of x squared dx. So if we apply our little formula, x squared is x to the n plus 1 is x cubed. We're going to divide by that new power over 3. We're going to do the same thing with the 2. The 2 comes out and I just have the integral of dx. So if I'm adding up all these little pieces of dx, that gives me just x. So 2x. So that tells me that my work function is x cubed plus 2x. That's how you would get your force. I'm sorry, that's how you would get your work from a statement of force. Now, if we're going to look at graphs, if we're going to look at a force versus displacement graph, and we look at that curve, the area under that curve is going to tell me about the work done by that force. That's what taking an integral is. It's finding the area. Likewise, if we look at this relationship, if we look at the derivative relationship, where force is the derivative of work with respect to time, and we look at that graph, if we have a work versus time graph, then the slope there, the change in work over the change in time, is telling me about my force. So the slope of work versus time is force. And if we look at this one, every time the slope is 0, my force is equal to 0. Now, the next thing we're going to look at is potential energy. Before we do that, we're going to look at conservative versus non-conservative forces. That's a really important thing on the way to looking at the potential energy of a force. So, for a conservative force, the work done by that force is independent of the path taken. The path that we take does not matter in the least when we're looking at a conservative force. So, take for example lifting up that mass a given distance. If we do that, the work done is mg, the force done by gravity. The work that we do is mg times our height. All that matters is how high we go. If, however, we start down there, we do something crazy and get to the same height, guess what? The work is still mgh. It doesn't matter how we get to that height. All that matters is our height. So that conservative force is path independent. Then we have a non-conservative force. Conservative, non-conservative, it's going to be the opposite. So for a non-conservative force, the work done by that force depends on the path that we take. Friction is a really good example of a non-conservative force. How far I go, the actual path I take, has a huge impact on the work done by friction. So, we're going to look at potential energy right now. Our big definition that always applies for potential energy is that is the work done against a conservative force. Anytime we do work against a conservative force, that work doesn't go away, it's just stored as potential energy. So doing work against a conservative force stores the work as potential energy. That's what potential energy is. Work done against a conservative force. So, looking at this, looking at what we've already said about kinetic energy, our big idea is that work is the thing that changes the energy of an object. So if an object has potential energy and it turns into kinetic energy, something had to do work to make that happen. If something has kinetic energy and that turns into heat, something had to do work to make that happen. If an object has kinetic energy and it turns into potential energy, something did work. Work is the thing that changes an object's energy. So we're going to look at a quick example of that. Let's say we have a mass. Say our mass is 4 kilograms. It's got a weight of 40 newtons. And I'm going to come along and pull up with a force of 50 newtons. I'm going to lift this object 7 meters. Why? Because it's a gross number that no one likes to multiply by. So, I'm going to lift with 50 newtons. Gravity's pulling down with 40. Things going up 7 meters. So, gravity does work. In this case, gravity is going to be the work done by gravity is going to be the weight, 40 newtons, times 7 meters. And it's going to be negative this time because the force is opposite the displacement. So gravity is going to do negative 280 joules worth of work. I, on the other hand, am pulling with 50 for a distance of 7 meters. So I'm going to do 50 newtons times 7 meters worth of work, or 350 joules worth of work. So, let's see what happens. In this case, the net work done on my object is 70 joules. So guess what? Oh, alright. The net work done on my object is 70 joules. The opposite of the work done by gravity is 280 joules. So my 350 joules did 2 things. One of the things it did was give the object a net work of 70 joules, which turns into kinetic energy. So the object now has a kinetic energy of 70 joules, and I did 280 joules worth of work against gravity. That turns into potential energy. Okay, so my work accomplished 2 things. We gained kinetic energy and we gained potential energy. So, looking at springs, this is important, trying to get the potential energy from springs, or really any other force that we have a formula for. So, I know that the spring force is negative kx. If I want to get the potential energy stored in a spring as a function of x, I'm going to have to take the integral of force with respect to x. So, for that negative sign, remember that work is the integral of f dot dx. Work is the change in kinetic energy. If I gain kinetic, I lose potential. So, potential energy is the opposite of work done by the force. My conservative force in this case is the spring. So, I'm going to need the opposite of that. Just like down here, we looked at the opposite of the work done by gravity. Here we're going to look at the opposite of the work done by the spring. That's where that negative sign comes from. So we will plug in negative kx dx. Negative signs go away and the k comes out. And now I just have the integral of x dx. So if we use our power rule, we raise it 1 power and divide by that new power. So my spring potential is 1/2 kx squared. I'm just going to use that little definition that we got from springs. And the way a spring works is if I displace that spring in any direction from its unstretched length, I'm going to store energy inside of that spring. And we can do this with any given formula for force. It doesn't have to just be for springs, but we use springs enough that it's good to go ahead and do that and say that's what it is. All right. Now comes the big show, conservation of energy. This one is super important. So, what we are saying for conservation of energy is that for any given system, the energy at one point is equal to the energy at another point. There's no difference in energy for any given system at any different point. It may change forms, but the total energy is going to be the same. So when we're doing conservation of energy type problems, regardless of the points that we're choosing, the energy is the same at all of those points. So all we're doing is choosing two different points and setting their energies equal to each other. And we hope to get the information that we want. So when we talk about mechanical energy, specifically we're talking about potential and kinetic energies. But we've talked about a couple of different kinds of potential and kinetic energies. So for right now, my total energy could be mgh. It could be 1/2 kx squared. And my kinetic energy is 1/2 mv squared. But we also have rotational kinetic energy. It's 1/2 I omega squared. We use I for rotational inertia. We use mass for linear inertia. So, there are different times when these things are appropriate to use, and there are times when it's not appropriate to use. So, mgh is our gravitational potential energy. We use this if an object is changing heights. If its height doesn't change, its gravitational potential energy doesn't change, and I don't need to put it here. Anytime my height changes, gravitational potential energy changes. When we do gravitational potential energy, we need to be sure that we measure from the center of mass of our object. If we don't, it's not going to be accurate. Okay? Most of the time we're talking about point masses, so this is a really easy thing to do. Every now and then we're talking about meter sticks that we rotate around a pivot point. In that case, we're going to need to measure our gravitational potential energy from the center of mass of the meter stick. 1/2 kx squared is only for springs. That's it. Anytime you have a spring and that spring gets compressed or decompressed, you're going to have to talk about spring potential energy. No springs, no spring potential. Problem solved. 1/2 mv squared is for translational kinetic energy. Anytime an object's moving, it's going to have translational kinetic energy. Now, because we're throwing in rotation stuff, there are going to be different times when it's okay to use translational kinetic energy. One of those times is when the center of mass of my system, or my object rather, moves. When the center of mass moves, the center of mass has translational kinetic energy. We're going to have to deal with that. If I have a block sliding across something, it's going to have translational kinetic energy. The center of mass is moving, my object is sliding. If I have something rolling, with or without slipping, and its center of mass is moving, then it's going to have translational kinetic energy, as long as the center of mass moves. You will not use this if my object is pinned down. If it's constrained in any way, this is not appropriate to use. So, if there's a pivot point, I am not going to be able to use translational kinetic energy. The specific example I'm thinking of is the rod hanging down that swings up or swings down. In that case, there's a pivot there, and it would not be appropriate to use translational kinetic energy for this object. Reducing it to its center of mass doesn't do me any favors. Now, 1/2 I omega squared is my rotational kinetic energy. We use it when something spins. If it's spinning, it's got rotational kinetic energy, we need to take it into account. So we're going to use if it's rolling, if it's spinning, or if it's moving on a pivot. In that case, we're going to talk about rotational kinetic energy. Now, I left something out. A lot of the problems that we do, we don't have to deal with this. But every now and again, we're going to have to deal with the work done by friction. In the real world, we have to deal with the work done by friction. So, the work lost to friction is just going to be force of friction times distance, mu mg times the distance that we're moving. And yes, we're going to add that to our total energy at the end. What that means is that some of my total energy had to go into the work of friction and not somewhere else. So if we look at it, the bigger the work of friction gets here, the smaller my kinetic energies are going to get. That's why we add it. It's a different place for my energy to go. And when we lose work to friction, when we lose energy to friction, it turns into heat. But no matter what, my energy is still conserved. It's just changing forms into heat. Friction did work, changed energy into heat. Now, last thing to mention is gravitational potential energy. We get to set it equal to 0 wherever we want. Doesn't matter. You get to decide. But the big important thing is they have to stay consistent all the way through. So if you pick the top of a system to be 0, it has to be 0 for every single point. And all the potential energies have to be measured from that 0 point. It's easiest to do it at the lowest point that your object goes. All right. That's all we have for this energy review. If you've got issues about simple harmonic motion and you want to talk, if you want to talk, come in and see me. But if you have issues with simple harmonic motion, watch those 2 videos. I'm not going to make another one for that. There's also a simple harmonic motion review video that has more information than you need, so don't go searching around for that. Okay, this is what we have. So if this helps you tonight, great. Otherwise, happy studying, and I will see you tomorrow for the test.